Convergent-divergent nozzles have been used in aviation for many years, whether in fighter jets or rockets. The physics of air in these conditions is fascinating, which is why we're discussing this topic again today. Nozzles. Hello, I'm Sergio Hidalgo, an aerospace engineer, and welcome to this video. This is the third in a series of, well, yes, it's the third, so we've already done two. By the way, I'll leave the link there for you. It's important to watch them as my explanations progress from simple to complex. This video, which is the third one, is absolutely crazy, so you definitely need to understand the previous videos. For those of you who are wondering, what do you have to tell me about nozzles? Well, my final project was to design a variable nozzle. So I think I have a lot to tell you about this topic, so let's get to it. A few weeks ago, I ran a channel survey asking what you wanted to know about nozzles. And the truth is that many of you have asked me things that, from my point of view, are easy to find on the internet. So as an aerospace engineer, I've done my work. My final project was about a nozzle. I think I know some really amazing things that are going to interest you. So all those questions you've asked me and that I'm not going to answer in this video, don't worry, because I'll answer them in the future. But before that, I think it's more interesting to understand how air works inside a nozzle. Well, the first thing is to answer a question that I left hanging in the previous video, and it's the following. Imagine that I had a convergent nozzle, but at the throat it extends. After the convergent part, it's simply a straight line. Now imagine I increase the pressure at the nozzle's start, just like before. There will be a certain point where Macuno will appear somewhere. Where? Where will Macuno appear? Here? Here? In both places? Will a shockwave appear? The truth is, I had no idea what was going to happen until he did the Y, right? Yeah. Why? The answer is that it's true, or why the answer is that it's not. Right, or the answer is that it's not, or why the answer is that it's not. The answer is that it's true or not. The answer is yes or not. The answer is no, and the is it true or not? And the answer is or not. And the answer is it true or not? And the answer is it true or not? Pressure at the beginning of the nozzle. Since we already have Mach 1 at the inner throat, we can't exceed Mach 1 as only supersonic flow is possible. If we have a divergent section, and that's not the case here, we don't have a divergent section then at the point where we have Mach 1 at the inner throat. If we keep increasing the pressure at the beginning of the nozzle, that excess pressure won't be able to be converted into velocity. That energy from excess pressure won't be able to be converted into velocity. Therefore, the air will carry that excess pressure with it. So, when it comes out of the nozzle, it will have excess pressure compared to the outside air, and this excess pressure also generates thrust. Airplane engines generate thrust by rapidly pushing large amounts of air backward. And also, if the air is coming out with more pressure than the ambient air, meaning the air surrounding the plane, that also generates thrust. Be careful, this is more complicated than it looks. This is clear from the equation for engine thrust. By the way, thrust in Spanish is empuje. So the first term we have is M. This M is the mass flow rate, which represents how much mass per second is passing through the engine. Then V is the speed at which the air is exiting. That is V exit, and then V in is the speed at which the air is entering the engine. Then we have the area, which represents the exit area of the nozzle. PE represents the pressure at which the air is exiting, and PN represents the ambient pressure, the pressure of the air surrounding the airplane. So here we can see that the thrust is given in two terms. This one here represents the part of the thrust that is given, because the airplane is throwing air backward very quickly. Because if you notice, what it's doing is, how much air are you throwing backward? The MX, how much have you accelerated that air? And in the that's why you multiply by the exit area, since that's where it is. Pressure equals force divided by area, so if we do pressure times area, we get a force. The first part of thrust is simple, the complication is in the second part. Due to the pressure difference between the engine's air output and the outside pressure. This only happens if the air exits faster than Mach 1. If not, the exit pressure and the ambient pressure would be exactly the same. Because physically, there can't be a pressure jump. I'll show you both the Mach number and pressure distribution analyses together to help you understand them better. As you can see, while we have subsonic flow inside the convergent part of the nozzle, the exit pressure is exactly the same as the outside pressure. However, the moment Mach 1 appears and we keep increasing the pressure at the beginning of the nozzle, that excess pressure starts to appear at the exit. Currently, this is because air is coming out faster than the speed of sound. The information can't enter from outside the nozzle to the inside now, because the air is going outwards, right at the speed of sound. So any information sent as a pressure wave can't get inside. And that's why inside the nozzle, when we have Mach 1 at the outer throat, the air has no idea what the outside pressure is. And that's why that excess pressure can appear. But the moment the air leaves the nozzle, it expands and that generates thrust. That's why, for example, in commercial airplanes, which typically don't have Mach 1 at the nozzle exit, this pressure thrust doesn't occur. Well, I hope you understood it, because it's incredible. I know it's a bit dense, but it's really super important that you understand it. Plus, what I'll explain next is even crazier. I found a National Aeronautics and Space Administration document where, well, actually it's not a document. It's a piece of a document that talks about the F-15's nozzle, which, by the way, the plane, sorry. The engine is a Pratt & Whitney known as the F-100, which is a convergent-divergent nozzle. The thing is, on page 211 it says that the throat area is determined by the values of pressure, temperature, engine rotation speed, and so on. Like I've said before, the plane is being confirmed here since National Aeronautics and Space Administration says so. The plane is constantly taking readings of the outside temperature, the inside temperature, the outside pressure, the inside pressure, the engine rotation speed, and so on. Based on that, it calculates the equation I showed in the previous video, which I'll show here. The throat area is to have more constriction at the throat so that the divergent part becomes supersonic afterward. But now comes the real magic. If we carefully read what it says next, we can see that the divergent part, meaning the exit area of the divergent part of the engine, will adapt by itself. Depending on the pressure conditions outside and inside the nozzle, it's incredible because with this, a lot of complexity is being removed from the nozzle itself to adapt this divergent part. Don't worry, I'll explain it to you. In a convergent-divergent nozzle, what you're always looking for is to expand the air inside the engine until it has the same pressure as the ambient air, that is, the air outside. So, an optimal divergent-divergent nozzle wouldn't have the second part of the thrust. If we take the equation, the second part of the thrust, the one that comes from excess pressure, we wouldn't have it because all that excess pressure in the divergent part would have been transformed into velocity. And in theory, this is better. In other words, it generates more thrust than a nozzle that's only convergent, which would have a bit of thrust from the first term of the equation and a bit of thrust from the second term of the equation. Should we revisit the document to review how the divergent part adapts on its own? Depending on the pressure conditions inside and outside the nozzle, we can see that it makes perfect sense. For example, if a plane is flying very high, the ratio of total pressure inside the nozzle to ambient pressure is much higher. Because when you're flying at high altitude, the ambient pressure is very low, so that ratio is going to be quite high. So in this case, since the ambient pressure is very low, it's going to exert little force on the walls of the nozzle. So they're going to allow the divergent part to open up a lot, and this will make the air inside the divergent part, since it's very open, able to expand a lot. But if now we have a plane that's flying very low, the ambient pressure is going to be much higher. So the pressure outside the pedals now won't allow the divergent part to open up as much. So since the divergent part isn't as open, the air will expand much less. As I was saying, it's a fantastic idea to make all of this automatic, depending on the air conditions. If we represent this on a graph where the x-axis marks the throat area, then the further to the right, the larger the throat area will be. On the other hand, the vertical axis represents the ratio of the exit area to the throat area. Remember, the exit area is the divergent part, so the throat area is always smaller. In other words, this ratio has to be greater than 1 no matter what, that is 1 point. For example, here it indicates that the throat area is about square meters. The exit area is about 1.2 times the throat area. That means the exit area is 1.2 times larger than the throat area. So more or less, the nozzle would have this shape. However, a point here. For example, it will have a larger throat area, but the ratio of exit area to throat area is the same. This would roughly have this shape as shown in the document's graph. And if you look closely, the bottom line represents the condition where the total pressure divided by the ambient pressure is 2.7. However, the top line has a value of 4. This ratio matches what I said before, so pay attention. Here's the summary. Convergent-divergent nozzles always expand the air until it has the same pressure as the outside air. In this curve, total pressure is 4 times the ambient pressure. That means it's quite high, so the air needs to be expanded a lot. That's why the divergent part is going to be very open to expand the air a lot. On the bottom line, with a ratio value of 2.7, the air doesn't need to expand as much, so the divergent part won't open as much.
Well, Yankee, in science, the truth is,
this video has been absolute madness of concepts. I mean, the things I've talked about are really very complex. But as I was saying before, I think this is truly the value that I can bring to the channel. I know all these things because I researched intensely. All the other things you ask me about the nozzle materials or how the mechanism works and so on. You can find all that online, but what I explained is complex. And I know it because since I had to design a nozzle, I had to deal with this myself. But it's not something everyone knows, and that's why I think it's very interesting to tell you about it. For those of you who found it very complicated, I recommend that you watch it again, but after some time, for example, in a week, so that your thoughts are clearer. And of course, make sure you've watched the previous 2 videos about tuberos, because if you don't have the concepts clear, it's impossible. Now it's your turn to answer the following question, which I'll address in a future video about tuberos. Is it possible for the air in a convergent-divergent nozzle to exit with less pressure than the air outside? I mean, we've seen that as long as the air is moving at subsonic speeds. If the air exits at subsonic speeds, its pressure matches the outside air. We've seen that the moment we have Mach 1 at the exit. If we still increase the pressure a bit more at the beginning of the nozzle, that will cause the air to have excess pressure. In other words, it will come out with higher pressure than the outside air. But could it come out with lower pressure? I'll leave the question there. I'll talk about that and much more interesting things in the next video I make, so give it a big like. If you really enjoyed this video, if you didn't know me before, subscribe to this channel. I'm convinced that all the content I make every week, because I upload a video every week, you're going to love it. If you want to contact me, you can do so via Instagram or LinkedIn. We have a Facebook group called Science Junkies you can join, the link is in the description. Just a reminder, I have a podcast where I discuss aerospace engineering. For those of you who want to support me, you already know you can do it through Patreon. Honestly, I really appreciate it because all these videos take a lot of work. Incredible. And
subscribe to
this channel and then you can watch this video here. You know, as always, above all, science lead.